Bueno, vamos a empezar. Muchas gracias a todos por venir a esta conferencia. A partir de ahora voy a hablar en inglés, por deferencia hacia nuestra conferenciante. So, on behalf of the Physics Faculty, welcome to another conference of the series Hablemos de Física, or Let's Talk About Physics. This is the first conference of the academic year, and we have today the privilege of having with us a speaker, Professor JOANNA HAIGH from the Imperial College London, who will talk about physics of climate change. This is a conference which is, as you probably know, is jointly organized with the Spanish Royal Society of Physics, whose president, Professor Adolfo Azcárraga, is sit here at the table with me, and also co-organized jointly with the Ramón Areces Foundation, represented here by Mr. Medina. I take this opportunity to thank both of them for their continuous and permanent support for organizing this series. I also want to thank, as usual, the Maths department for allowing us to use this conference hall. We hope to have our own one, not late, let's say in a couple of months or so. So hopefully the next conference in the series will be in the physics building. So our speaker today is a worldwide expert on climate physics. She has an impressive academic career, which will be detailed now by the Professor Azcárraga. All I have to say is thank you for coming and giving us this, I'm sure, this nice talk. I'm sure you will enjoy the talk, and also given the topic and its implications, its social implications beyond the scientific ones, of course, I think that they will be particularly stimulating for our students, for whom this conference series is actually motivated. So I will now hand over to Professor Azcárraga, who will make a more detailed account of the speaker's biography. Thank you very much.
Thank you very much. When the Paris agreements were signed, I thought that the problem of climate change deserved to have a conference of the series, because it is a problem which is affecting everyone, many countries, and in fact in Europe, Spain will be particularly affected. So I thought of inviting a real expert. You know that the problem of climate change is a problem in which everyone has an opinion, but not a well-based opinion. So immediately I thought of Professor JOANNA HAIGH, who, among other things, has written the scientific assessment for the intergovernmental panel on climate change. And she immediately accepted, which was very kind of her. And now I will make just a comments about her career. She read physics in Oxford, where she also obtained the PhD, or excuse me, I should say DPhil, and then ended becoming professor of atmospheric physics at the Imperial College. She's also the co-director of the Grantham Institute for Climate Change and Environment. And as I said, she has written the scientific assessment for this panel on climatic change, which has, so to speak, two sides. There is the scientific side and the political side. The political side has to work on the information which is presented to the people who have responsibilities in government by the scientists. She is well known by discovering some aspects of the way in which the sun affects our climate. And because of his contributions to physics, she was given what it is called a CBE, which means Commander of the British Empire, and she is also a Fellow of the Royal Society. So we are really happy having here an excellent speaker, which is going to give, no doubt, a very good overview of the problem, the consequences, what can be done, what should be done, and so on. This problem of the climatic change goes very much back in time, because I think that the first person who noticed that CO2 was producing an increase of temperature was a chemist, or rather a physical chemist, named Svante Arrhenius. Those of you, I see that most of the people here are very young and maybe did not read Jules Verne in their youth when they were even younger, but in the novels of Jules Verne, Svante Arrhenius, the chemistry of Svante Arrhenius appears more than once. But he was an optimist because he thought that the increase in temperature would be very good, the climate would be more benign. After all, he was living in Sweden, so he thought that an increase in temperature would be good. But the reality was quite different, and in fact, I think it was Roger Revelle, an oceanographer, who in the 1950s said that in the 21st century, which means now, there will be violent changes because of the greenhouse gases. Of all this, we'll give an account our speaker, and so in order not to take more time, I will just pass the microphone to the representative of the Fundación Ramón Areces, who is sponsoring this series of talks. So,
thank you. Lo primero que quiero darle la bienvenida a esta conferencia que, como han oído, se encuadra dentro de este ciclo de conferencias que viene realizando durante años, de Hablemos de Física, y que organiza la Royal Society of Physics de España y el Departamento de Física, con el soporte de la Fundación Ramón Areces. Como probablemente todos conocen, la Fundación Ramón Areces fue establecida hace ahora 40 años por Ramón Areces, que después de crear la cadena de grandes almacenes del Corte Inglés, decidió dedicar su patrimonio a una fundación que lleva su nombre para la promoción de la ciencia española. En este sentido, los que somos herederos de esta filosofía de Ramón Areces estamos llevando a cabo sus objetivos a través de varias iniciativas. La más importante, digamos, la primera, es la promoción directa de la ciencia a través de proyectos de investigación que versan sobre los más diversos temas. Hemos hecho desde ciencias del suelo hasta biomedicina, por supuesto, física, en varios de los concursos. En segundo lugar, la Fundación Ramón Areces tiene como obligación promocionar a los jóvenes científicos que quieren ir al extranjero para realizar becas postdoctorales. De hecho, dentro de los temas de las becas postdoctorales ha figurado durante muchos años este tema que hoy vamos a tratar hoy, del cambio climático, que ahora hemos ampliado a un nombre un poco más amplio, como es el de preservación de la biosfera. Y por último, Ramón Areces estaba preocupado cuando fundó esta entidad de que la ciencia española era buena, pero era poco conocida fuera de nuestras fronteras, y por lo tanto ha promocionado mucho durante estos años el establecimiento de cambios de ideas entre científicos de fuera, del extranjero y de España. Y dentro de estos deseos, pues, de traer el conocimiento a España, lo mismo que llevar el conocimiento español al extranjero, se encuadra este tipo de actividades que hoy llevamos a cabo, como es la conferencia de la doctora JOANNA. Finally, I would like to thank Professor Joanna HAIGH for coming to Madrid and to deliver this lecture that we all follow with more attention.
Thank you.
Thank you.
So we go down and let the speaker begin.
Check this once. Yes. Is this on now? Yeah. Okay, am I on? Yes. So first of all, I'd like to say thank you very much to the Royal Society, to the Department of Physics, and indeed to the Foundation for giving me this opportunity to come and talk to you. It is indeed an honour and a pleasure to give this talk and also to have the chance to see a bit of Madrid. So I'm going to talk to you about the physics of climate change, but I'm going to try and put it in context. So this is the sort of structure of the talk. I'm going to, first of all, mention and then think about what the factors are that are influencing climate change, some of the natural factors and also some of the human factors. Moving on from that to say, well, this is how it changes. What impact does that have on basically on the way we live and how we can carry on society as we do at the moment? And finally, think a little bit about what's going to happen, what might happen in the future, and how we can respond to that or indeed try to mitigate against those effects. So this is a very messy graph. It's showing as a function of time along here, so 2,000 years. And this is a temperature anomaly of the northern hemisphere at the surface. And you can see it's very messy. And that is because going back in time, we don't have proper scientific temperature measurements, thermometers. So these records have to be deduced from what are called proxy indicators. So, for example, the width of tree rings, or ratios of isotopes of oxygen in ice cores, or other indirect measures of what the climate was doing. And each of these different curves has used a different proxy indicator to reconstruct the temperature time series. So there's very wide range of variations, but there's a general agreement that it sort of went up a bit warmer to about the year 900 or 1000, then it went a bit cooler to around sort of 1600, and then it's gone warmer more recently. And the black little bit at the end here is actually where we do have the instrumental record, and the measurements have been collated from across, in this case, the northern hemisphere, to really give a northern hemisphere record of a temperature change in temperature. So the question is, how much is it changing? Can we assess what are the forcing factors? And can we use computer models to simulate these impacts and predict what's going to happen into the future? So now if we look a little more recently, we're now looking at this instrumental record. So this is a collation of temperature measurements from 3 different sources here. And they are pretty much in agreement within the grey, which is the assessment of the error or the uncertainty range. So you can see that it's sort of flat here, then it goes up a jump and it flattens off, and now it's going up, and it'll flatten off here and it's going up again. So the first thing to note is that it's not a smooth increase. And indeed, we wouldn't expect it to be a smooth increase because the climate system is a huge, wonderful, noisy, real system. It's a complex system. And anybody here that's a mathematician or works in complex systems, you'll know there's no way it's going to behave in a very well-behaved way. And indeed, as a physicist, it's much more fun to be investigating something that's a little bit more unpredictable than something that just does something very obvious. There's much less of interest in the physics associated with that. So when people sometimes say, oh, well, I will show you some maps of carbon dioxide in a minute, but they sometimes say carbon dioxide is going up and up and up smoothly, but the temperature is not going up smoothly, that's not a reason to discount CO2 as cause of climate change. But I'm getting ahead of myself a little bit. So we want to understand quite why this increase is taking place. And this is other evidence for climate change. So surface temperature is one indicator, but there are other indicators. Some are more certain than others. Oops, sorry, didn't mean to do that. One which is well known is the sea level. So as the temperature increases, the major immediate factor is the heat gets absorbed into the upper ocean, and there's a thermal expansion. And most of this increase in sea level is due to thermal expansion of the water in the oceans. Of course, as the temperature gets warmer and ice on land, not sea ice, because that makes no difference to sea level, but as ice on land, continental ice melts, that will also contribute to sea level rise, and it could be huge, but the contribution at the moment is smaller. So you can see how sea level rise has gone up by perhaps 20 centimetres over the last century. This is the heat that's in the ocean rather than the air. It's going up. This is Arctic summer sea ice. So there's ice floating on the surface of the oceans in the Arctic around the North Pole, and it has a seasonal variation. There's more in the winter and less in the summer. And this is a measure of the summer amount, and the summer amount is decreasing. Again, not uniformly, year on year, it wiggles around a bit, but the overall picture is quite clear that the summer sea ice is decreasing, and there's various people's estimates of when it will first disappear in the summer. That's uncertain, but you can see the trend. And this one's a bit more noisy. This is snow cover in the Northern Hemisphere. So when you hear about global warming of the temperature increase, this is not the only sign that we've got global effects of climate change. And this is another important point, is that just when we say global warming, that means global average temperatures. It doesn't mean that it's going to be the same everywhere. So in fact, it's very much not that. And you can see this is an estimate of temperatures across the globe. And this is, it was actually the difference from 2015 from an average of this 30-year period. And you can see the largest warming is occurring in continental land areas, especially northern ones here, and in the west of the American. But it's not warming everywhere. And indeed, in the North Atlantic and over the east seaboard of the United States, it's actually colder that year. So what we have is not a uniform warming, but some overall warming, but it can have patterns which are changing over the globe. So again, if you were to be somewhere in Ireland, and you can say here, actually it wasn't any warmer, there's no global warming. You can say there's no warming in Ireland, but you can't say there's no warming across the globe. So we have to be careful when we use phrases like global warming, what it is we actually mean. So when we think about what's controlling the climate, we look at the radiation balance of the climate system. And what we have is radiation coming in from the sun, and that is essentially the only energy source for the climate system. There's a tiny, tiny, tiny amount coming from the Earth's core, but it's really negligible in this context and on these timescales. So there's energy coming in from the sun. Some of that gets reflected back to space. The rest of it gets absorbed at the surface. The surface warms and emits heat. And so this is the solar radiation in yellow, and this is the heat radiation in grey. The surface emits heat, and a lot of that gets absorbed by the atmosphere. So the atmosphere itself, of course, is material, and it emits heat downwards and upwards. But this essentially here is greenhouse trapping, and I'll come back to that in more detail. But you can see that anything that affects any of these branches of the radiation budget will influence climate, or has the potential to influence climate. So changes in the sun would influence climate, or indeed changes in volcanic eruptions. So when there's a big volcanic eruption, it throws a load of material up into the atmosphere, and if it can get up into the stratosphere, that's above the weather systems, it can stay there for perhaps 2 years. it reflects sunshine to space, and there's well-documented evidence for climates being slightly cooler in years after big volcanic eruptions. So this is represented here by that little bit there. So those are both, of course, natural components. And then we think about the human components. There's first of all the greenhouse gases. I'll go on to those in a minute. There's also industrial aerosols. So these are particulates that are put up into the atmosphere by human activity. In particular, sulfur dioxide from power stations, which gives you sulfate aerosol particles, and they act exactly like the volcanic aerosol that I was just describing. So when you have more aerosol, it makes the planet slightly cooler. And you can also change the planet by changing, for example, land use. So if you were to change agricultural patterns to make the surface brighter, perhaps you were chopping down trees or something, that would make the surface brighter. That would again increase reflection of sunshine to space, and that would tend to cool the planet. So there's all these different balancing effects, and what we need to understand is quite how each of these is contributing on the timescales of relevance. So I'm just going to say a little bit about solar radiation here, partly because it's, I think, interesting physics. And of course, on very, very long timescales, we take into account the fact that the Earth's orbit around the Sun is varying. So the orbit is an ellipse, and it varies according to three fundamental parameters. One is the eccentricity of the orbit, that is how elliptical it is or how far away from a circle it is. The next one is the tilt of the Earth's axis. So the axis of the Earth is tilted into this ellipse. So as it goes around, you have northern hemisphere summer over here and southern hemisphere summer over here. So this is giving us the seasons. And that tilt varies around on timescales of around 40,000 years. The eccentricity varies on timescales of around 100,000 years. The final parameter is what's called the precession, and that is a change in the time on this elliptical orbit at which the northern hemisphere, the North Pole will be pointing in towards the centre. So it happens at the moment that the North Pole is tilting in towards the Sun when the Earth is furthest from the Sun on the elliptical orbit. But that doesn't need to be the case. On timescales of around 20,000 years, that tilts slightly. So at some later time, you'll find that it's the southern hemisphere has a summer when it's further away from the Sun. So there's all these timescales which are just due to the changes in the Earth's orbit around the Sun. And this is just looking at the radiation getting in at the top of the atmosphere. This is not on thousands of years timescales. This is 1 year. And we've got the seasons, the months along here, January to December. And this is latitude going up here. So this is radiation at the top of the atmosphere. And you've got very strong seasons at high latitudes, weaker season in the tropics. And the point of including this picture is to show you the hemispheric asymmetry. So if you look, you can see that there's a larger red blob in the southern hemisphere here than there is in the northern hemisphere, and that is due to this precession, where the northern hemisphere summer is actually when the Earth is further away from the Sun. So we need to take account of these changes, which are significant, so 3% or so changes in the solar radiation coming in to the Earth, as a function of season and as a function of latitude. So back to the long time scales. This is a record of temperature from an ice core in Antarctica. And you can see this record is doing this. And these are periods of ice ages. And so you see they're happening on something like 100,000 year timescales. And it's believed or understood that these are related to changes in the eccentricity of the orbit. So this is natural produced climate change due to these orbital variations on these very long time periods. You might say, why is this not a sort of harmonic, smooth function? I'll come back to that in just a minute. So first of all, let's consider the greenhouse gases. And first of all, I'll come back to other greenhouse gases in a minute, but I want to introduce carbon dioxide. And what I'm going to show you now is several time series of carbon dioxide concentration as a function of time. And each of these plots will have a different time period. So this one is just over the last 5 years. This is in parts per million. So it's 400 parts per million. That means 4 molecules of carbon dioxide in every 10,000 molecules of air. And you can see there's an upward trend, but if you look, there's also an annual cycle. And the annual cycle is due to the fact that there's more land in the northern hemisphere than in the southern hemisphere. The land's got vegetation. The vegetation in the summer absorbs more carbon dioxide than it emits, and so there's an annual cycle due to the vegetation, that which is clearly marked, but it's on an upward trend. This is now the same thing, but going back 50 years, and you can see this upgoing amount concentration. These measurements are actually taken in Mauna Loa in Hawaii, so this is a very clean air. It's not very little industrial pollution, for example, so this is clean air in the middle of the Pacific Ocean. So you can see that it's going up from 320 to 400 of these parts per million units over that 50-year period. And I'm going to show you more graphs. These have different vertical scale to these, but all these three have the same vertical scale, and they're stopping at 380 and starting at 180 parts per million. This one is exactly the same plot as that, but with this different vertical axis. This one is now going back 1,000 years or so, and you can see the little red bit there is that one or that one, now squashed up in time. And going back 1,000 years, the concentration is around 290 parts per million and not really changing very much over that period. Here we've got it, I don't know if you can see this, this is 1,000 years, 10,000 years, pretty flat concentration. We've got some more plots here. These two have the same vertical scale as these ones. And this may look familiar. This looks like the temperature plot I showed you just now. So the carbon dioxide is going essentially with the temperature, and I'll come back again to that in a minute. This one is millions of years, now 10 million, 20 million years, and you see we're still on the same vertical axis here until you get sort of 20 million years. And this last one now is hundreds of millions of years, and the vertical scale is much, 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 much higher. So when you go back 100 million years and more, the concentration of carbon dioxide in the atmosphere is much, much higher than it is today. But let's try and put that in context somehow by what's life on Earth doing. Well, modern humans appeared on Earth about 200,000 years ago. The first Homo species appeared a few million years ago, and the first primates appeared perhaps a few 10 million years ago or something like that. So what we can say is that life on Earth has not been the same as it is now, anything like the same as it is now with these high levels of carbon dioxide. So the continents were all in different places and the life was different, everything was completely different when we had the very high levels of carbon dioxide. So we are in a very different state now than we have been ever before. So you might say, well, I said 4 molecules in every 10,000 doesn't sound very much. You know, how can it actually do something? So now we're going to look at the spectrum of the radiation. I referred before to the solar radiation and the long-wave radiation without saying much about the wavelengths of that radiation. This is a spectrum of the long-wave radiation leaving the atmosphere. So we have wave numbers along the bottom here, or this is microns along the top here. And this is a spectrum. If you had a surface at 21 degrees with nothing else, black body function, it would look like this red curve. The actual observed spectrum looks like this shaped curve here. And there's two things to notice about this. One is that it's quite different from the black body emission, and that's because there's gases in the atmosphere that are absorbing it. And we identified the gases here and here and here, and I'll come back to that in a minute. And also the peak of the radiation is something like, say, 10 to 15 microns. And you'll see this big bite here of carbon dioxide. And the important thing to note here is that the main constituents of the atmosphere, which are nitrogen and oxygen, have no effect on these wavelengths at all. Oxygen absorbs in UV wavelengths, nitrogen at microwaves, but these gases have no effect on the radiation these infrared radiation that's coming through the atmosphere. So this is a bit of a more delving into the physics. So this is, I hope you can see that. This is calculating the effect of the different gases on the outgoing radiation. So you see these are all negative values because the presence of the gas is stopping the radiation escaping. And each coloured curve represents a different gas. And so this is saying, what's the water vapour doing? Well, it's trapping about 71 watts per square metre of the radiation that's trying to get out. So water vapour is the most important greenhouse gas in the atmosphere, and indeed it is absolutely fundamental to life on Earth. The presence of water vapour makes the climate about 30 degrees warmer than it would be were it not present. So it makes the climate a nice place for humans and plants and everything to live. So we can't live without the water vapour just from a temperature point of view, apart from all the hydrological cycle and all that aspects. So water vapour is the most important greenhouse gas, but it's sort of constrained. So if you get a warmer atmosphere, it can hold more water vapour. If you put more water vapour in the atmosphere, it causes a bit of warming, but it's essentially constrained by the fact that it'll drop out. The capacity for the atmosphere to absorb water vapour is constrained, and it'll precipitate out. So you can't just carry on increasing water vapour into the atmosphere ad infinitum at the temperatures that we're at. The second one here is carbon dioxide, and that does about a third of the amount of water vapour. And that's now in this sort of pale green colour. And this is the water vapour in the red here. And it just so happens that the strongest carbon dioxide effect takes place where there's little water vapour absorption. And those of you that are experts in molecular spectroscopy will probably be able to tell me more about that than I can tell you. But it's basically to do with the way that the molecules rotate and vibrate and absorb and emit radiation at particular frequencies. And it just so happens that CO2 has this thing called a rotation vibration band around 15 microns here, which is very strong, where water vapour doesn't do any absorbing. What this means is that increase in the carbon dioxide can actually have a larger effect than you might have thought sort of a priori. There's other gases. Ozone does about 7 of these units, and methane and nitrous oxide. And indeed, increasing concentrations of these gases on the climate is also contributing to the global warming. But I'm not going to say anything more about that now. So why does carbon dioxide do something even though it's only 4 molecules in 10,000? Because it has absorption at wavelengths that just happen to be where there's little absorption by other gases, and it's also near the peak of that black body function, so that it just happens where that most of the radiation is going up, the CO2 is doing the most absorbing. So it's just the way things are. And what that means is that if you increase carbon dioxide, you get a bigger warming effect. So going back to this plot again, so we noted that the temperature, and we noted the carbon dioxide. And you'll sometimes hear, we won't get too political about this, but people who could be called climate change deniers saying, oh, we've seen it all before, CO2 goes up, temperature goes up, it's all natural. Unfortunately, this plot is not at all reassuring. It is quite the opposite. Because what we have here, these changes are driven by changes in the Earth's orbit around the Sun. So it's forced by the Sun. The temperature starts to go up. As the temperature goes up, carbon dioxide is released from stores in various oceans and ice and around the planet, the carbon dioxide goes up. That's a greenhouse effect. That makes it warmer. That means more is released. And so that is why you get this very sharp increase in response to the sort of more smoothly varying solar. And then when the sun sort of goes back, I say the sun, you know what I mean, the orbital changes go back, then we go back again, and we go back into the Ice Age. So on these very long time scales, carbon dioxide is acting as a positive feedback on the initial solar-driven forcing. So this is not a reassuring picture. In fact, if you've got something that is forcing climate change, in this case it's the sun, but anything else, it could be human carbon dioxide, this sort of positive feedback will take place. So it will enhance the original forcing. So on to the computer models. I've got to check how much time I'm using. So we use computer models for forecasting the weather and also looking at understanding the climate. And with apologies to the physicists here, this is going to be a little bit elementary. I hope nobody minds, but you'll see why. I want to put some equations in. So we'll start off with Newton's second law, and I won't test you. Force is mass times acceleration, or acceleration is force per unit mass. So we're considering what forces act on a parcel of air. And the forces are essentially gravity, pressure gradient. So if you've seen a weather map, you know you get low pressure regions and high pressure regions. Everything else being equal, the air will try to move from the high pressure region to the low pressure region. So we've got a pressure gradient force. But then we have to take account of the fact that the Earth is rotating, so it doesn't move directly. It actually moves round the pressure. And also we've got to take account of friction. So where the air is going over rough surfaces, it will be slowed down. And you can express that in this format here, where this is the wind, this is the acceleration, gravity, pressure gradient, Earth's rotation, and friction. Next one is conservation of mass. So you can say what goes in must come out or get squashed. Here we are. That's the getting squashed, and that's the coming in and going out, divergence of the wind. It's all right, there's only 4 of these. I'm not going on forever. First law of thermodynamics, so conservation of energy, essentially. If you add heat to the air, it'll get hot, or it might expand, depending. And so here's that one. Here's the adding in a heat. Here's the getting hot, and here's the expansion. And finally, here I'll put the ideal gas law, so an equation of state relating some of these other variables. So why have I included all these equations? Well, to show that if you write them all down, and now I've colour-coded the variables, what we've got essentially is 6 equations in 6 unknowns. It's 6 because the wind is a vector, so it can go north, south, east, west, or up and down. So it's essentially 3 momentum equations. 3 wind, and so 6 unknowns and 6 equations. So that's like simultaneous equations. You can solve it. And that's essentially slightly oversimplified, but that's the basis of weather and climate forecasting using computer models. Of course, the issue is, one of the issues is we've got to specify this heating and also the friction, so it's not quite as easy as I was suggesting. We solved the equations on a 3D grid, and you will hear the weather surfaces are always wanting better and better computers and more powerful computers so that they can make these grids smaller and smaller and smaller and resolve more and more high resolution physical features. So we solve the equations on each of these grid points a step forward in time, and that's essentially a weather forecasting or climate model. And just do an example. I mean, you've all seen the weather forecasts, but this is from the rather wonderful European Centre for Medium-Range Forecasts. This is today's chart. At midnight last night, you can see the pressure patterns in the contours, and the colour is a representation of the temperature through the lower atmosphere. You can't really see the geography, but Spain's down here somewhere. So this is what it was like last night. This is the analysis. That is the forecast from 3 days ago to today. It's pretty good. You know, eyeballing it, you can't see much difference at all. This is a forecast from 10 days ago to today. And so you can see that they've got the high pressure over Spain, they've got the low pressure over northern Europe, but the actual details of the patterns are slightly in the wrong places. So in terms of weather forecasting, 10 days is probably about the limit of what can usefully be done at the moment. People from Met Services may disagree with me here, but I think that's probably about it. So, the physics seems okay. You might think it's okay. I've certainly presented it as it's sort of very easy and fundamental. So why aren't weather forecasts perfect? Well, of course, the real atmosphere is not a cubic grid. And you have to take into account all these wonderful things like clouds and the latent heat and the orography and all the rest of it. So I was oversimplifying a bit on the cubic grid. And the smaller you can make the grid, the more that you can resolve these processes. But you'll never get down to the last frictional, viscous, dust devil on the space scale of about a few meters. So there's always going to be some approximations in those very, very small features. You've got to do clouds and rain. I'm not going to say anything more about that. You've also got to do initialization. So every time you start a model forecast, you start from somewhere. And of course, you start from your today's weather, but you can absorb extra data that's coming in from satellites and aeroplanes and all the rest of it to make sure that your current state is more accurate for your next forecast. And this is hugely important because if you start somewhere slightly different, you can forecast the wrong direction. So here's an example. This is well known in the UK. There was something called the Great Storm of October '87. You can see some of the effects here. Very, very strong winds over the southeast of England. The British Met Office famously had somebody on television who said, "Oh, there's some woman, has to be a woman, stupid woman, who's rung us up and said that she's heard there's going to be a hurricane. Don't worry, dear, don't worry." There's not. The point is, this lady was in Guernsey, and she had heard the French weather forecast, who had forecast it, and the UK weather forecast didn't. And the issue was they'd missed some of the data from over the Atlantic, so their initialization was different and incomplete. And so the forecast went way off. So that's important. Talking about weather forecasting now for the initialization. And now we're going to talk about weather and climate. So if you can't predict the weather, more than 10 days ahead, how can we possibly say anything about the climate 10 years, 20 years on? So what we have to understand now is that when we predict the climate, we're not saying that the weather in Madrid on the 5th of October 2022 will be such and such. No, we can't do that. But what you can say is that the climate of Spain will be likely such and such a temperature within an uncertainty range over that, over a particular season. So what you're doing is you're predicting typical seasonal values over larger regions. You're not trying to predict precise weather forecasts over very, very long timescales. And that's demonstrated by these plots. What we've got here is two plots. In both plots, the black curve is the observations. That's the temperature measurements I showed you earlier in the talk. But there's coloured curves here in both, which are climate model simulations. So they're called hindcasts because you're forecasting what happened in the past. On this side, there's only natural forcing, so only the sun and the volcanoes. And on this side, it's got all the forcings in, so it's also got the greenhouse gases and the aerosols and all the rest of it. So one thing you notice is that there's a big spread of predictions. But the other thing is that you can see that the observations deviate from the predictions from natural forcing about, say, 40 or 50 years ago, and you can only get that broad agreement by including the human forcings. Going back to the whole thing about complexity, there's lots and lots of wiggles on here because each of those wiggles is a different climate simulation initialized from a very slightly different, even very slightly different starting point. And you can see you start from different starting points and you get different evolutions. If you compared one of these wiggly lines with another wiggly line, they're not the same. But you can see that there's an envelope of agreement. So here it's this envelope and here it's this envelope. And that is how we predict into the future what the climate change might be like within a range of uncertainty. And this is a sort of average value in the middle. Now, of course, the Earth is not an average. The Earth is on one of these wiggles, or possibly none of them, but something like one of those wiggles. And so it can be going around all like this. So if it's not warmer in 2016 than 2015, for example, that's really not at all surprising. It just means it's wiggling around with this complex system. But you can see that the general, route of travel is going up here with the global warming. So I said that. So if we're going to predict climate into the future, we've not only got to use these complex models, we've also got to predict what the carbon dioxide is going to do. And of course, that means predicting human economy and all the rest of it, which is way outside my expertise. But when we do this, so there's the Intergovernmental Panel on Climate Change, which is a huge body of scientists which writes these reports every few years into the state of the climate. And it prescribes various scenarios or representative concentration pathways, RCPs, of what energy usage and might be like in the future. And here's some examples. So there's the RCP 2.6, and you can see that's not so much coal, or some coal, but a lot of bioenergy. This is the sort of worst one here, is a huge amount of coal and oil and not much more or less bioenergy. So you make different assumptions about the energy usage. And then you come up with different CO2 emissions. So if we just stick at looking at the green one, which is sort of the best one, and the blue one, which is the worst one of these scenarios, you can see the carbon dioxide with the green one, it goes up to about 2020, then it drops down. So CO2 emissions are going to zero by the end of the century. The blue one, CO2 emissions are going up and up and up and up. Now, emissions is one thing, but of course concentrations is another, because the lifetime of carbon dioxide in the atmosphere is several hundred years. So although this emissions stop and go sharply down, the concentration is very slow to respond, and it hasn't got down to 400 again by the end of the century. So we've got to think about that. When we think about doing something about it, remember, it's a long time scale. You can't just decide something today and it'll happen. It won't. It's going to take a long time. And if you do this blue one, which is essentially business as usual, it's way up, going way up. So these are predictions for those two RCPs in sea level change up to the end of the century. This one is stopping at about 1 metre. This is going up to... sorry, this isn't sea level. This is global surface temperature. This is about 1 degree, and this is going up to 4 or 5 degrees. Oh, right, I'd forgotten I put this one in. This is a slightly complicated picture, but it's quite important to understand. So what we've got here is the cumulative total emissions. So that's saying all the CO2 that's been emitted by human activity up to a particular date. And that's the temperature change corresponding to that total CO2 emission. And you can look at these different scenarios and how they pan out on this plot. So the blue one, well, first of all, we got the actual observations, and that's the black here. So we've emitted, half a gigaton, half a trillion tons by this year, 2010, and the temperature's gone up by very nearly 1 degree. Then we look at these things into the future. If you choose the better one, it's going up here by 2100. It's got to about 800 here, and it's nearly 2 degrees. If you choose the sharp emissions, 8.51, it goes shooting up here by 2100. You've got nearly 5 degrees and that amount of CO2. So the interesting thing about this plot is, actually, you don't really need to know details so much of where it's come from, just to know that it's the total amount of CO2 that's been emitted that's actually causing the temperature change. So if you were to decide that you didn't want to exceed 2 degrees of warming, which has been suggested as a dangerous threshold, then you can't go above 1 trillion tons, essentially, of CO2. So if you burn it up, the sooner you burn it up, the less likely we are to be able to stay below 2 degrees. This is, again, to make the point about the long time scale of the response. So I've made this point already, really, but even if this sharp one, if you stopped it and dropped the emissions very suddenly to nothing, this is probably about the year 2200 now. It takes a very, very long time for the concentrations to come down. Here's the temperatures flattening off slowly. Everything's very, very slow. So more difficult is to predict the regional patterns. It's sort of relatively easy to predict global average changes, but if we're going to be interested in the impacts of climate change on our lives, then we have to try and do this on a sort of regional basis, because as I said, it's not the same over the globe. So what we have on the left here is a sort of better pathway, on the right here is the worser pathway. The top here is temperature, and the bottom here is precipitation. Where you see these sort of hashed lines, it means that it's very uncertain. We can't really, range of uncertainty is too large to say anything. Where you see the little spots, that's considered to be better understanding, so outside 2 standard deviations, I think it is. So obviously, there's a lot more warming. Again, it's distributed unevenly over the globe, and we've got this little bit of not so much warming, and indeed over here cooling over the North Atlantic, which is quite interesting. It's probably due to changes in the ocean circulation. Large increases over the land. So if you look, for example, over Africa here, it's something like 7 degrees over North Africa. Precipitation, you see, if you just go to 2100 on this pathway, very difficult to say much. It's all a bit uncertain. But if you use this stronger pathway, by the time you get to 2100, it's still uncertain in certain regions. But for example, there's quite strong confidence in drying over the Mediterranean and over Spain. So you can see a much drier climate is anticipated if we go down one of these high CO2 pathways. Interesting thing, there's more rainfall in some places, and indeed there's a suggestion, for example, that the Indian summer monsoon will be more intense in response to climate change. And something that's not shown here at all, and I'm not actually going to cover, but the extremes of the behaviour, so extreme events like very, very hot days, extreme rainfalls are more likely to occur when you've got this higher. So that's an impact is different than just the average. Oh, this is just to make the point. This is actually the average surface temperature at the moment. So I was talking about North Africa. Currently is about sort of 20-odd degrees up here, annual mean temperature. So if you add on another 7 or 8 to that, you can see it's getting really pretty unbearable to live there, even worse than it is at the moment. So not something that you'd want. This is the sea level plot that I was jumping ahead to earlier. So this is predicted changes in sea level over these different pathways. So this better one is about 0.5 metre by the time you get to 2100, and this one is going up to nearly 1 metre by 2100. And if you would carry on going and melt all the land ice and things, it's tens of metres. So it's serious stuff. Another thing that you'll sometimes hear climate change deniers say, which is true, is that when there's more carbon dioxide in the atmosphere, the plants like it, and they will grow more because they've got more carbon dioxide. That's true, they do, but also they have to respond to the temperature changes, and there is a limit temperature above which certain plants can't survive. So here we got some food plants. And if you just look on the right here, lethal limits, and by the time you get up to 40 degrees, none of these plants can survive at all, and they're severely restricted in growth at some quite much lower temperatures. So although the plants might like the CO2, they're not terribly impressed by high temperatures. This is some estimates using the high emissions pathway of these sort of climate impact. So increase in heat waves. So this is, you might say, hang on a minute, that's a very large number. This is percent exposures, so there's more than one heat wave in a year. This is numbers per year that will be heat waves increased. Water scarcity, of course, in regions that are drying out. Flooding, where you get intense rainfall events. Plant species lose habitat, and cropland. Of course, cropland can move, so it might just move northwards. So you have to be careful about this sort of analysis, but certainly it will change. And so this is a project which was trying to look at avoiding dangerous climate change. What can you avoid by taking some action? So again, we've got an extreme pathway here. This is CO2 emissions, and a one that stops by the end of the century here. And this is the bad scenarios that I showed you just now in terms of heat waves and crops and flooding and water stress. And if you were to do this one, you can see it would be better. But it's not the same on all these impacts. And in fact, in water stress, it's all taking place already. So this is an important point. So sometimes, you can argue about whether or not you want the temperature to stay below 1.5 degrees, 2 degrees. You might even think you don't mind it going up by 5 degrees. But I don't think anybody would be happy with the idea of it going up and up and up and up forever. And the only way that you can stop the temperature going up, is to stop the CO2 emissions. Or counteract the CO2 emissions in some way or other. So it's, even if you're happy with 5 degrees, you've got to stop the CO2 emissions at some date, even to stop at 5 degrees. So we cannot carry on as we are forever without boiling. Right, now, how much time have I got left? I can't see Jose. He's timing me. Okay. So what can we do about it? What can we do? Well, the first thing is we could adapt to the impact. So there is a certain body of argument that says, actually, we should just adapt, put up with it. It's easier and cheaper to adapt than to try and do something about it. And that may be possibly even true if you're living in a fairly benign, perhaps in Scotland or somewhere where the weather's, and we heard about Sweden earlier, perhaps the Swedish people might like it a bit warmer, but there's other things they might not like the melting ice. But you can make that argument. But of course, if you're living in an island in the tropical oceans, some things can't adapt. If you're underwater, you can't adapt. That's just, you have to go somewhere else. That's your adaptation. So it's slightly arrogant of people in the rich northern world to suggest that everybody else in the world can adapt to their CO2 emissions. What else can we do? We can try and do something else to compensate. This has become known as geoengineering. And the idea is that you do something to try and compensate for the evils of CO2 emissions. There's various ideas, some of which are just plain mad. So here's one. Put giant mirrors into space. They reflect the sunshine back and cool the climate. You might think this is science fiction. There's people actually working on designing these things in the United States. It's not one big mirror, it's lots and lots of tiny little ones. But you've got to keep it, anyway, I get upset when I start talking about it. You can do sensible things. Sensible things, grow more trees to absorb the CO2. Of course, there's nothing harm in that. One that's taken quite a bit of interest is seeding clouds. So you put particles, a bit like the volcanic aerosol, up into the atmosphere, and they act as cloud condensation nuclei, and you get more clouds, and the clouds are brighter, so they reflect sunshine back to space. You can do things like putting iron into the oceans. So the idea is that the plankton that live in the oceans like iron as a nutrient, and they grow more, and when there's more plankton, they absorb the CO2 out of the atmosphere. There's been some field trials of that, and it's not really very successful. There's other things like taking the CO2 out of the atmosphere and sequestering it onto rocks. All sorts of ideas. It's an engineer's, heaven. They can think of all sorts of plans, but I think it's just avoiding the main question. And the real thing, what we should be doing, is reducing the emission of greenhouse gases. So I'm going to sort of finish off now saying a little bit about the international agreements on climate change. So Jose mentioned the Paris meeting that took place before Christmas last year. This is the United Nations, F.Físicas, COP21, the Conference of the Parties, the 21st meeting. So they meet every year, but every sort of 6 years or so they have a very bigger meeting. The previous one was in Copenhagen in Denmark, and those of you may remember it was a huge disappointment at Copenhagen. They agreed absolutely nothing. It was really, really very disappointing. So coming up to Paris, we were all thinking, oh, you know, what are they going to do this time? But it was organised rather differently, and people, different countries had to submit their proposals for how they would reduce their CO2 emissions. And in fact, countries covering 97% of the population did that, including the EU. And an agreement was reached. Now that is absolutely amazing. For a start, an agreement was reached. It was unanimous. 195 countries agreed unanimously that something should be done. Wonderful. I mean, after Denmark, after Copenhagen, that was just such a... It was just really, you know, amazing. So the agreement is to try and keep a global temperature below 2 degrees, actually try to do 1.5 degrees, but you know we're nearly at 1 already. And then do something to deal with the impacts. So of course this is to help out the low-lying islands and things like that, who, you know, it's impacting them already, and provide finance to do that. So from the rich countries to the poor countries. In December, they all agreed. And as I say, that was absolutely amazing. But then you sort of, in the cold light of day, you think, OK, they've agreed, but are they actually going to do it? Are they going to do anything about it? But as of a week or so ago, 77 parties or countries have ratified the agreement, which means essentially that it's going to enter into force. It enters into force on the 4th of November this year, and the next COP starts on the 7th of November. So that means that the treaty is come into force, and now we can all start thinking, you know, actually practically, how are we going to achieve these reductions? We don't have to argue about whether we're going to do it anymore. We're really going to do it, but how are we going to do it? Who's going to do what? And that's going to be the nub of the arguments now. There's various... So this is called Mission Innovation, and 21 countries have committed to investment in clean energy, so you know, less carbon fuels, which is good. This is billions of dollars of investment. There's also a lot of engagement with the private sector, so you might think that businesses would be, you know, really against this, but they're not. So many of them can actually see it's in their interests to do something. And they generally welcome the COP22. They largely want carbon pricing, which is a whole another economic argument. And then there's a sort of private coalition of companies, big companies, led by Bill Gates, working to invest in clean innovation. So that's my conclusions. I won't read them out, but just to say it is a huge global problem. But we're moving in the right direction. It just needs a bit more impetus and engagement of people to make sure it doesn't get to the really bad state. So I'll leave it there. Thank you.
So many thanks, Joanna. It's been a beautiful talk. Before we ask for questions, I would like to make a comment on the great storm, because I was in England at the time. And I remember the fiasco of the forecast, but then the next day, or in the next 2 days, when the same weather forecaster who had made a mistake had to recognize that he was wrong, then he imposed a penance on himself and sang in front of the audience Stormy Weather.
Oh, yeah.
You know this song, Stormy Weather? So he sang as a kind of...
penance, yeah.
Okay, so now the talk is open for questions. Please.
Yeah, my question concerns, like the IPCC said that 2 degrees Celsius increase in temperature was kind of a critical point. And as we know in this like complex systems, as we were talking about, there's like stable attractors, right? Like we could say that our climate right now is quite stable and predictable. But I wanted to know what's the scenario for, I mean, if we go further, like if we if we get to that 202 degrees Celsius, what's going to happen? There's going to be like an abrupt change in climate, or it's going to be rather smooth, or what's going to happen if we go further than 2 degrees Celsius?
That's, I mean, a very good and interesting question. The 2 degrees is not some sort of absolute threshold. Nothing happens at 2 degrees. There's no difference between 1.9 and 2.1. It was just chosen as a sort of idea that that's when sort of you begin to really get the signal from the noise. But of course, so there's 2 degrees is prescribed. You will notice that actually some people wanted 1.5 degrees, and that's written into the agreements. But you know, it would be great if we could achieve that. But I think the chances of it happening are very slim. We're already at 1 degree, and the national contributions are not getting anywhere near even 2 degrees. So they've got to really come down to get to 2 degrees, let alone 1.5. So just to finish up, so your point about using computer models to forecast into new regimes is a very good one. Yeah. So, of course, as I pointed out when I was talking about the structure of climate models, you need to include parameterizations for things like clouds, convection. And these have to be based on our understanding of the current. I mean, based on the physics, of course, but in there will be some parameters that are based on how it happens at the moment. And it's a very important point that we need to keep checking those and making sure that we aren't prescribing something that's only related to essentially the current situation and won't be able to do the future. The only good thing to say about that is that the sort of hindcasts, if you compare what's happened with modelling the past, the correspondence between, at least on global averages, between the measurements and the models is pretty good. And we do predict not just the means, but also the spread, so the extreme events. So your point is absolutely a good one. I mean, in terms of the complexity of the system and whether we're getting outside of our regime of competence. I think people are aware of that, but that's not to say complacent about it.
So is our planet Earth resilient enough not to? I mean, we're not expecting any regime shift or anything like that in recent years?
People talk about one regime shift that was discussed. I mentioned a little bit about the North Atlantic Ocean. And there's a lot of talk. I don't know if anybody saw the film The Day After Tomorrow, which is very entertaining. It was based on the idea that the ocean circulation, overturning circulation, stopped, and so that the North Atlantic got very, very cold. And so there's been quite a lot of work on looking at changes in ocean circulations. And it might be slowing down a little bit, but there's no suggestion at the moment that it's anywhere near stopping or likely to stop soon. The other threshold, of course, relates to ice. So when you've melted the ice, you make the surface darker, I mean, at least over the sea. That means that there's less solar reflection, which means it's warmer, which means, you've got a positive feedback that way. So you could imagine there's a sort of threshold of no ice. But again, that's not predicted in the next decades.
Okay, so we can be sure that chaos is not coming in.
I hope not.
More questions? Comments?
How much is in the model probability, and how much are there intervals? Because I think they are equivalent, not exactly equivalent. It seems to me that the models are right, but the initial conditions are our personal choice. So, well, there is always a bias. If you are optimistic, then you choose one model, if not another.
Well, that you could do that. I mean, I would say in argument to that those spaghetti plots that I showed you included a range of different initial conditions, all of which are within the bounds of plausibility. So you have to start from somewhere. You have to start from something that you think is a real, plausible situation. You wouldn't choose something that looked like Mars to start your initial, because that wouldn't be reasonable. So you have a range of starting conditions. In terms of choosing models, of course, there are a number of different models across the world, and they have different horizontal resolutions, they have different representation of the clouds, of the physics, of the radiation. And I think that's quite healthy in the sense it means we do have a number of different perspectives. Again, you can't be complacent because they're all essentially based on the same assumptions. And if there's something we haven't thought of that should be in there and isn't, then none of them has got it. But at the moment, I think, we're in terms of the breadth of uncertainty, I think we're fairly okay.
Hi. Well, first thing, thank you very much for your talk, because it's very, very difficult to say so much in so short time.
Oh,
so
sorry.
thank you very much.
Oh.
So one question related to the last intervention. Could you say something about the chaotic aspect of the atmosphere and therefore the effect on the forecast system?
Yes. Yeah.
Because I think it's good to students know how the forecasting system overcomes this difficulty. And what is the reason of the probabilistic results from the models?
So thank you for your kind comments.
Yeah, because it's related to the observation the professor said before,
Yes.
because really,
Yes. So the system is inherently complex, and as we've already mentioned, it has to start from somewhere and evolve. So I presented some results from the European Centre for Medium Range Forecasts. I didn't say about them, they also do ensembles of forecasts. So with their 10-day forecast, I can't remember now how many is in the ensemble, perhaps 200. So they're starting off from 200 different, might not be that many, I can't remember, different states, and this is giving their spread of uncertainty as they go forward. And it's essentially down to the complexity of the system. You talk about the butterfly wings in West Indies or something and affecting the climate over the other side of the Atlantic. And there is that in there. It is in there. But if you look on the sort of envelope, and that's your 95% confidence interval or something like that.
Other factors such as the solar activity, for instance, which is unpredictable to a good extent, and I think they can have an influence.
He's asking about solar activity.
Yes.
And I haven't planted this question. This is my own research area, so I will not I will not give an hour's lecture on that. So that when I was talking about the Earth's orbit around the sun, of course, that's changing the amount of radiation that gets to the Earth and its distribution over the globe, but that's just assuming a constant sun sitting in the middle. But the sun is variable, and you know that we get sunspots. People have observed sunspots since, there's a very good record in the Paris Observatory, hundreds of years of observations of sunspots. There's a sort of quasi-11-year cycle in sunspots. And there's always been a talk about, does solar activity affect the climate? So back in the 1930s, I mean, the idea is quite plausibly, I mean, if the sun's energy is going more and less, of course it would, wouldn't it? It's our main source of energy. The question is how much is the energy varying and how might it be affecting the climate? So back in the 1930s in the United States, they had various radiometers measuring the solar radiation, and they put them up mountains to try and make the air nice and clean. And they tried to measure the solar radiation and watch how it changed with the sunspots. And in fact, they thought that when the sun was more active, when there was more spots, black spots on the sun, less radiation coming out. So when there was more, that it would be anti-correlated. Actually, they couldn't get any correlation at all. And that was because even though they were up mountains in clean air, they've got the atmosphere above, and it's just the changes are too small. So over an 11-year cycle, the change we now know, because we've got satellites outside the atmosphere measuring, it's about 0.1%, which is about 1 or so watts per square metre. Averaged over the globe, it's about 1/6 of a watt per square metre, which is sounds small, it's a small fraction. But then we think radiative forcing due to carbon dioxide, doubling the carbon dioxide gives you 4 watts per square metre. So, 1/2 a watt per square metre or something is much smaller, but it's not nothing, it's not insignificant. So I think the latest understanding is that changes in the sun have a very minimal effect on the climate, on those sort of global average timescales. Certainly you can't find any change in the sun's energy that would give you the warming over the last 50 years or so. But there's some really interesting physics, atmospheric physics, to do with solar ultraviolet radiation heating the stratosphere and affecting the climate below. And that's what we're doing at the moment. We're trying to understand that because it actually has effect on regional patterns, and particularly over the North Atlantic. So that's a great physics question, but I don't think it's going to come up with the answer that climate change is due to the sun or anything like that.
Another question. just one question is, what about variations in the position of the magnetic pole? Which I have read that
Yes.
that might influence too. Could you say
So the question relates to the change in magnetic poles. So when I was talking about solar radiation just now, I was talking about electromagnetic radiation. I wasn't talking about particles. And of course, solar particles, and indeed particles coming from other galaxies and all sorts of things, get steered round in fact, the magnetic field of the sun and the magnetic field of the Earth, and they tend to land at high latitudes, and that's why you get aurora, because the particles are precipitating at high latitudes. And there's a certain amount of discussion about the effect that these particles might have on the climate. And indeed, there's been observations that when you get this big solar storm, lots of particles coming in, you can, for example, deplete ozone at high latitudes in the stratosphere. So it definitely has an effect on stratospheric chemistry and on composition, but there's not much evidence that it's having any effect on the surface climate. Again, current research, but I don't think it's going to do much.
I'd like to know your personal opinion about the goals in the future for the climate control. Particularly, I would like to know if you are optimistic or not.
Depends how tired I'm feeling. I like to be optimistic. As I say, when that agreement happened in Paris, couldn't have believed it was going to happen. And now it's been ratified less than a year later. It was a unanimous agreement that none of these things has happened in any United Nations treaty before. This is all quite remarkable. So that's really good. And we've got the business people wanting to be involved. But the devil is how to do it. So I think it will come about because, I hope, people who are in business or in engineers, and they understand there's the opportunities. So it's not just, we can't do this, you have to do this, you stop using cars, you can't do this, it's all bad. It's, wow, opportunities. We can invent new clean energy. Businesses can earn money from inventing new clean energy. We can have clean air, like in China, they have all the air pollution, which is due to burning coal. We can have clean air as well as less CO2. And just looking at all the positives, the ongoing effects of doing these things, the effects on health. If you aren't breathing in poisonous air, it's much better for you. If you're not using your car and you're going on your bicycle, all these things, they're sort of positive additions. And I think this is the way to make it argue. So that's not a prediction, it's a wishful thinking.
Thank you very much.
Well, I did notice one of your final transparencies, this optimist note on the fact that people might think that protecting the climate might earn money. But all this has to be transformed in political action.
Yes.
And on the whole, I think that there will be more spending than earning money. So do you really think that there is a cause for optimism? Because in the past, it didn't work. Tokyo agreements were not implemented, for instance.
I'm not an economist, and nor am I an engineer really, so I can't really say about that. But what it requires is a will, and the government's will is determined by the people's will. So you look at what's happened with smoking. Who would have thought, at least in the UK, that we would have no smoking in public buildings? Extraordinary. But what happened was there was a general acceptance that it was bad for you to smoke, and then they changed the law. It was easy. There was no problem with changing the law. So it's just a question of getting it into the mindset of the government that something needs to be done, and then they can see the advantages of doing it.
Well, okay, let's hope so.
Let's hope so.
Okay, so let's thank the speaker once again. Thank you very much.
Thank you.